Hello and welcome to What's Genius, the channel where we interview the greatest scientists in history. Today we have a very special guest, Christiaan Huygens, the Dutch mathematician, physicist, astronomer, and inventor who is regarded as a key figure in the scientific revolution. He founded the wave theory of light, discovered the true shape of the rings of Saturn, and invented the pendulum clock, among many other achievements. Let's get to know him better and learn from his genius. Hello, Christiaan. Thank you for joining us today. How are you feeling?
I'm feeling well, thank you. It's a pleasure to be here and share some of my thoughts and experiences with you.
Great. Let's start from the beginning. How did you become interested in science and mathematics?
Well, I was born in the Huygens 1629 into a wealthy and influential family. My father was a diplomat and advisor to the House of Orange, and he also had a passion for art, music, and literature. He encouraged me and my four siblings to pursue our interests and talents from an early age. I was especially fascinated by geometry and mechanics, and I learned from some of the best tutors in the country, such as Frans van Schooten. I also read a lot of books by famous mathematicians and philosophers, such as Descartes, Fermat, Pascal, and Galileo.
What were some of the first problems or questions that you tried to solve or answer?
One of the first problems that I tackled was the problem of points, which is about how to divide a prize fairly among players who have different chances of winning a game. I wrote a letter to Pascal about this problem when I was only 16 years old, and we exchanged several letters on this topic. We both developed some of the foundations of probability theory, which is now widely used in many fields of science and engineering.
That's impressive. What about physics? How did you get involved in that field?
Physics was always a natural extension of mathematics for me. I wanted to understand how nature works, and how to describe it with mathematical laws. I was particularly interested in optics and mechanics, because they deal with light and motion, which are essential for astronomy and engineering. I was inspired by Galileo's discoveries with his telescope, and I wanted to improve his design and make my own observations of the sky.
And you did. You made some remarkable discoveries about Saturn and its moon Titan. Can you tell us more about that?
Yes, Saturn was a mystery for a long time. Galileo had seen something strange around it, but he couldn't make out what it was. He thought it might be two smaller planets on either side of Saturn. I used my improved telescope, which had better lenses and a longer focal length, to observe Saturn more closely. I realized that what Galileo had seen were actually rings around the planet, which changed their appearance depending on their angle to the Earth. I published my findings in 1659 in a book called Systema Saturnium.
And what about Titan?
Titan was another discovery that I made with my telescope. In 1655, I noticed a small star near Saturn that moved with it across the sky. I realized that it was actually a moon orbiting Saturn, the first one ever discovered. I named it Titan after the ancient Greek gods who were the ancestors of Saturn.
That's amazing. You also made some important contributions to mechanics, especially regarding pendulums and collisions. How did you come up with those ideas?
Well, I was always curious about how things move and interact with each other. I wanted to find simple and universal principles that could explain all kinds of motion. For example, I wondered why pendulums swing with a constant period regardless of their amplitude or weight. I derived a formula that related the period of a pendulum to its length and gravity, which is still valid today. I also invented the pendulum clock, which used this principle to measure time more accurately than any other device before.
And what about collisions?
Collisions are another example of motion that can be described by mathematical laws. I studied how bodies bounce off each other when they collide, both elastically and inelastically. I found out that there are two quantities that are conserved in any collision: momentum and kinetic energy. Momentum is the product of mass and velocity, and kinetic energy is half the product of mass and velocity squared. These quantities can be used to calculate the final velocities of colliding bodies.
That's very impressive indeed. You also developed a new theory of light that challenged the prevailing view at the time. Can you explain what your theory was?
Sure. The prevailing view at the time was that light was a stream of tiny particles that travelled in straight lines. This was the theory of Descartes, who was a great philosopher and mathematician, but not a very good physicist. His theory could not explain many phenomena of light, such as reflection, refraction, diffraction, interference, polarization, and double refraction. I proposed a different theory, based on the idea that light was a wave that propagated through a medium called ether. I used the principle of Huygens-Fresnel, which states that every point on a wavefront can be considered as a source of secondary waves that spread out in all directions. By adding up these secondary waves, one can find the shape of the new wavefront. This principle can explain all the phenomena that Descartes' theory could not.
That's very fascinating. How did you come up with this idea?
Well, I was influenced by some experiments that I did with sound waves. I noticed that sound waves could bend around obstacles and interfere with each other, creating patterns of loudness and silence. I wondered if light waves could do the same thing, and I tested this hypothesis with some experiments of my own. For example, I used a thin wire to create a single slit for light to pass through, and I observed the diffraction pattern on a screen behind it. I also used two slits to create an interference pattern of light and dark bands. These experiments confirm my wave theory of light.
That's very impressive. You were ahead of your time with this theory. How did other scientists react to it?
Not very well, unfortunately. Most scientists at the time were still attached to Descartes' theory, and they did not accept my wave theory. They thought that light was too fast and too small to be a wave, and they did not believe in the existence of ether. They also did not have the instruments or the mathematics to verify my theory. It took almost 2 centuries for my theory to be fully recognized and developed by other scientists, such as Young, Fresnel, Maxwell, and Einstein.
That's a shame, but you must be proud of your legacy and your influence on modern science.
I am proud of my work and my discoveries, but I also know that science is never finished. There's always more to learn and more to explore. I hope that future generations will continue to pursue the truth and the beauty of nature with curiosity and creativity.
Thank you very much for sharing your wisdom and your genius with us today, Christiaan. It was an honor and a pleasure to talk to you.
Thank you for having me. It was a pleasure to talk to you too. And remember, maten is wetten.
And thank you for watching What's Genius. If you enjoyed this episode, please like, share, and subscribe to our channel for more interviews with the greatest scientists in history. See you next time.